Second speaker, second and last speaker, is also from the Institute for Advanced Study in Princeton, Nima Arkani. Now, Nima comes in some sense from the other end of theoretical physics. He made his name as the premier phenomenologist of his generation, exploring the possibilities of new physics beyond the standard model. But as Robert described, the kind of physics that goes under the name of string theory or fundamental physics unites all of these different approaches. And Nima has made extraordinary contributions, not just to the ongoing attempt to extract clues and truths from nature directly, but also to speculate on the deeper meaning of possible new ideas like string theory. And so he combines both day-to-day interaction with our experimental colleagues, who are the backbone of science always, with the more speculative aspects of string theory and quantum field theory. You know, in elementary particle physics, LHC will shortly, within a day or two, report the results from the last run with much more data than they had previously. And all of us are waiting with trepidation, expectation as to what will be announced next week in Chicago at the annual meeting of the high energy physics community. Nima's going to tell us. I hope, perhaps. If not, he will tell us about the future of elementary particle physics, and I hope, in particular, from the experimental point of view and from the point of view of China. Nima is not just a member of the Institute for Advanced Study and a theoretical physicist, but he also has been playing a very important role in, he's the director of the Institute for blah, 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 at the Institute at the IHEP in Beijing, which is, I hope he will describe that institute, but it is part of the international collaboration where many of us, and especially Nima, are trying to help the very ambitious and enormously exciting proposal to build a future high-energy accelerator in China. So, Nima.
Well, it's a fantastic pleasure to be here. Do I need to use this microphone?
Yes.
Okay. It's really wonderful to be here. Thanks so much for the very kind introduction, David. So indeed, okay. So I want to tell you a little bit about the future of fundamental physics. Really, there's two big parts of this future. In particle physics and cosmology, I'll mostly concentrate on the story about what the future is going to be in particle physics. Well, as you've seen this kind of a picture many times before, also in Robert's talk, we live in a big, beautiful universe. There's a huge number of amazing phenomena that go on from the very largest distances where we observe things, around 10 to the 28 centimeters, the size of the observable expanding universe, down to distances around 1,000 times smaller than the nucleus of the atom, around 10 to the minus 17 centimeters. Almost every decade between here and there is filled with some interesting phenomenon or other. And one of the wonders of our understanding of nature that we gained in the 20th century is that everything that we see here, and probably more besides, is governed by some very simple underlying laws, four basic interactions: gravity, electromagnetism, strong and weak nuclear forces, which hold sway over this enormous range of distances. And this picture also represents the obvious frontiers of fundamental physics, where we just go to the boundaries wherever they are. We look at the very largest scales through experiments in cosmology, and also at the very, very smallest scales by doing experiments at very large particle accelerators. Now, this is going to be a talk about the future, but what puts a great backdrop to the subject is really the triumph of the 20th century. And I want to spend a little bit of time talking about this from a somewhat broader brush, bigger picture point of view than is sometimes done, because I think you'll see better what very zeroth order, deep, difficult issues we have to struggle with in the 21st century. It's not just a matter of details or one or two extra little bells and whistles on top of what's come before. What's at stake is really qualitatively different and new. And we can best appreciate that by understanding the really powerful things that happened in the 20th century. And this is really a summary of the triumph of the 20th century. Is in the beginning of the 20th century, we learned two big things. We learned about relativity and quantum mechanics. And by the 1930s, it was clear that both things were true. But it turned out to be almost impossible to build even candidate laws of nature that are compatible with these two big principles, the idea of space-time from relativity and quantum mechanics. It's so incredibly difficult to put those principles together that the broad structure of what the world can possibly look like at long enough distances compatible with these principles is almost entirely dictated. Okay? So on the one hand, these two big revolutions make the structure of the universe roughly inevitable at long enough distances. That, on the other hand, puts in particularly sharp relief the central dramas of the 21st century, that we have reasons to suspect that there's something wrong with these basic underlying principles that gave us these triumphs in the 20th century. You heard a lot from Robert about the idea that space-time is going to have to be replaced by something else because of very simple thought experiments involving quantum mechanics and gravity. It's even conceivable that we'll run into limitations of quantum mechanics when we attempt to apply the laws of quantum mechanics to the entire universe. So that's, on the one hand, just in the very theoretical foundations, the two big ideas, space-time and quantum mechanics, are under pressure from various thought experiments that are thrust upon us from things that we see in the world around us. On the other hand, there is another question that seems much more down to earth, and we'll spend most of the talk talking about, which is that one of the most salient features about the world, which we saw vividly on the first slide, is the universe is big. And you would think we know all these fancy things about the world and how all these things work. You would think we'd have a good answer to the question, why is the universe big? And why does it have big things in it? Big things like the Earth and elephants and humans and things like that on the Earth. Okay? Why is the universe big with big things in it? It turns out we have a lousy answer to this question. Okay? And trying to find a good answer to this question is another one of the major challenges of the 21st century. So, a quick redux of what I just told you, that relativity in quantum mechanics largely makes the structure of the laws of nature inevitable. The union of these two principles, the theoretical structure that started to be developed in the 1930s, and really took a lot of the rest of the 20th century to properly develop, and we still keep finding amazing surprises and mysteries inside it. The union of the set of all theories that are compatible with relativity in quantum mechanics is called quantum field theory. And one of the basic amazing facts about it is that we understand that everything in the world is made out of particles, and the particles interact. The most relevant possible interactions they can have, the most important interactions they have, are fundamentally the simplest possible interactions they can have, namely three things coming together at a point in space and time. If you think about it, that's the simplest possible interaction you can have. You can't just have two things coming together. You have something moving in a straight line. Well, it could just change its label and be called something else if it moves later, but that's just a change of name. Okay? the most fundamental interaction you can possibly have is three particles coming at a point together in space and time. So that's the simplest possible interaction, and amazingly it turns out it's the only interaction that we need to describe everything we see in the world around us. All the interactions are associated with little stick figure pictures like this. Electricity, the electric and magnetic force involve a stick figure interaction, three particles coming together of two electrons and a photon. The gravitational interaction, let's say that acts on electrons, is two electrons interacting with a graviton. And we're instructed to glue these three particle processes together over and over and over again in every myriad of possible way. And that's what gives rise to the extraordinary richness and complexity and diversity of all the phenomena we see in the world around us. But it all boils down to these amazingly simple things. Three particles coming at a point together in space and time. Now, we discovered gravity and electromagnetism were known to ancients. We discovered fancier things in the late 1800s and the early 20th century. We discovered the strong and weak nuclear interactions. And the big triumph of the development of the standard model of particle physics that David played such an important role in is the realization that while at long distances it looks like these other interactions are totally different than gravity and electromagnetism, when you go to high enough energies, which allows you to probe short distances, by Heisenberg's uncertainty principle, to probe short distances, you need very high energies. But when you go to high enough energies, you see the structure is essentially identical. There are some important details that are different, but once again, the strong interactions involve quarks inside a proton coming together and banging into a gluon, which holds them together inside the proton, again, at points in space and time. And the weak interactions involve similar things between electrons, neutrinos, and particles called W and Z particles. Now, in the case of these W and Z particles, we just didn't notice that this was what was going on, because these particles are very massive, and so you need very high energies in order to make them and see that this is actually what's going on, that you have these basic three-pronged interactions. But once we go to high energies, we see indeed that is all that's going on. Now, another important feature, so A, the interactions are as simple as possible. The dominant interactions are as simple as possible. Three particles come together at a point in space-time. B, the elementary particles have another property. Now, probably many of you, if you're in high school, you know that particles have mass and maybe they have charge. They have another important property, which is that they have an intrinsic kind of angular momentum, or spin. Now, because of quantum mechanics, the quantum in quantum mechanics means many things are quantized, and one of the things that's quantized is the amount of this intrinsic spin or angular momentum that anything is allowed to have. They have to come in multiples of 1/2 of the famous Planck's constant. So the allowed things, according to quantum mechanics, could be 0, 1/2, 1, 3/2, 2, 99/2, a million. Okay, they're all allowed. And yet what we see are just incredibly simple things. We have an electron that has a spin 1/2, the W particle has spin 1, the photon has spin 1, the graviton has spin 2. We don't see any of these things with spin 99/2 lying around. Okay, so that's just what I explained. Now, the specific detailed menu, so that's what everything boils down to. You have to tell me who are the particles, what are their spins, and which three of them come together at points in space-time and with what strength they interact. What we discovered by the mid-1970s is that there's a particular menu of these pictures out there. Okay? Now, we're not going to go through this in any detail. It's a little bit complicated, but it's not very complicated, and it's basically the same picture over and over again. We have some of the particles you're familiar with, maybe like electrons, or up and down quarks, or other things that you may be less familiar with, tau particles, charm quarks, and so on. It's a small table of all of these things, and everything is summarized by saying which three particles come together with what strength interaction. Okay, so now we can ask, why did it turn out to be so simple? There are two aspects of this. Why is it that the simple fundamental interactions were just three things coming together? Why don't we have fundamental interactions that are 12 things coming together, or however many that thing is? See, if we had that would be terrible. Okay? Because it would mean that there would be some irreducible complexity in the world that we can keep beating down until it finally got down to the most elementary possible process. We'd have to have a fundamental 100 particle interaction together. Okay? That would be awful if that was true. It's not true. Very interesting. Also, why do we have such a tiny menu of spins? We're allowed by quantum mechanics to have, those spin million particles. Why don't we have them? Why do we have this tiny menu of spins? And this is one of the really amazing things that we've learned in the past 30, 40 years, and we've been appreciating more and more in the past 20 or 30 years. And it's an example, in fact, it's a prime example of the basic point I was making, that relativity in quantum mechanics puts our imagination in an incredible straitjacket. Almost completely determines what nature can look like at long enough distances. So here's the claim, and in a different talk, I would spend most of the talk trying to explain this claim. It's actually possible to explain it in a public talk, but I won't do it today. You'll just have to believe me. So here's the claim. Let's say you handed sufficiently competent theoretical physicists, so probably not me, okay, but let's say you handed some of the people in this room these basic laws, and you locked them up in a room. Okay, you took them into the woods, you locked them up in a room, you closed the windows, you did not let them look at the world outside. Okay? Now this doesn't really make sense because they're in the woods, which is the world, and so on, but never mind. Okay? They don't actually know what the world looks like. And you hand them the laws and you say, go, make laws compatible with relativity and quantum mechanics. Okay? Well, if you did it to me, I would work on it for a week and I'd say, I'm sorry, it can't be done. Okay? By the way, why can't it be done? What makes it hard? What makes it hard is that the main thing relativity changed about the world is that time and space are treated on a more equal footing. So what one person thinks of as purely two events that are separated in time, another person might think of as events being separated by some combination of space and time. So relativity mixes space and time together, on the one hand. Now, quantum mechanics changed everything about the world. We can't predict the future, we only can predict probabilities and so on. But the one thing that it didn't change is the importance of time. In order to figure out what happens next, you have to specify what happens now and evolve in time. So the languages are essentially different from each other. That's why it's not easy to build things that are compatible with both of them. So that's why I would give up. But these other guys that wouldn't give up, that ask for more graduate students and more food, and that keep working and working, and eventually they would come up with the following amazing conclusion. They would say, look, we don't know, we haven't looked at the world outside, but we thought, and we figured out at long enough distances, whatever we're going to see are particles that interact. The dominant way they interact is with three of them coming together at points in space and time. And interestingly, we thought it was impossible, but in fact it's possible, but only for a small menu of possible spins. Particles that spin 0, 1/2, 1, 3/2, and 2. And then if they'd say that 2 is a really weird guy, you can't have 2 of them, you can only have 1 of them. And furthermore, the strength with which it interacts with everything is exactly the same, and when it acts on massive objects, it makes them go around in circles and ellipses. Okay, it's gravity. They've never seen that, they've never seen apples fall. Okay? But they can deduce the existence of gravity as one of the possibilities of putting together special relativity and quantum mechanics. Now, I've put in black here the particles that we've actually seen with those spins. Electrons spin 1/2, photons spin 1, this unique graviton spin 2, and in red, the particles that are not familiar, which are allowed by these basic rules, but which we had not yet seen. We'll come back to the 0 and the 3/2 in a second. So this is typical of the daily life of a theoretical physicist, is that you ask what nature can do compatible with the broad principles that it has. And at every given moment in time, you have some puzzles and mysteries, and you have to look at what nature can do. You can't dream up any old thing. There's a very constrained set of possibilities that nature can do, and then you can see within the menu of what's allowed, is there something nature hasn't exploited yet that it may exploit to help you and solve some of these problems? Okay, that's a theme that we'll come back to. All right, so far, this is all very rigid and wonderful. Nowhere have I mentioned anything about the famous Higgs particle. So you all heard back on July 4th, 2012, we discovered the Higgs particle. So what was the big deal with discovering the Higgs? Actually, the story of the Higgs is very intimately related to the story I just told you, because everything in this very rigid story, part of going to long enough distances means that you imagine Well, we imagine, we learned that in order to understand the dynamics of particles, we have to go to really high energies. So really, really high energies where all the mess and the details of their masses don't matter. Okay? When the energies are very high compared to the masses of the particles, you would think at some first order of approximation you can just forget about their masses because the energies are so high, and that's where the laws are simple. And it's precisely there where the particles can be treated as massless that their interactions are so completely nailed and rigid and given by these rules. So that sounds very nice, except for one important, very crucial difference between massive and massless particles when the particles have spin. So imagine we have a massive particle that has spin 1, like that W particle. Okay? Now what does it mean? That means that the particle is like sort of spinning like a top, but no matter how fast it's moving, you can catch up with it, and in the frame where it's moving, where it's at rest, if it's spinning up, if you tilt your head, you can imagine that it's spinning in all three possible directions. So the number of possible degrees of freedom, the number of possible different ways that the particle can spin when it has mass is 3. However, let's say the particle is massless, like a photon. Well, you probably all know either from early, well, this is China, so you probably learned this in junior high school. But whenever you learn it, you know that photons only have 2 polarizations, right? And if you talk about, or electromagnetic waves only have 2 polarizations, and if you go down to the particles, the photons have only 2 helicities. Why? Because we can't catch up with them. We can't do this argument that we said when they have a mass. Because they're moving at the speed of light, we can't catch up with them, so we can't tilt our head and make them point in every possible orientation. Massless photons have 2 degrees of freedom. Massless spin 1 particles have 2 degrees of freedom. Massive spin 1 particles have 3. And there is a qualitative, amazing, distinct difference between massless and massive. So we thought that, well, we just go to very high energies, we neglect the masses of the particles, and then the story is completely nailed by the structure of relativity and quantum mechanics. But it turns out that because of this difference, if we just applied that to everything we've seen, all the elementary particles we've seen, including the W particles and the Z particles and so on, that there was a simple mismatch between the number of degrees of freedom that we saw at very long distances, very low energies, compared to the number that was needed to build any possible consistent theory at very high energies. So we had to smoothly melt into this correct class of theories at very high energies, and we simply couldn't do it with the degrees of freedom that we had with the particles that we'd seen before. The amazing thing is that it just took a single elementary particle, one thing, single elementary particle, the Higgs, to fix it. And that one particle was all that was needed in order to be able to smoothly meld the world of the massive at long distances and low energies into the world of the approximately massless at very short distances and high energies. That's the story of the Higgs. Now, the Higgs was discovered at the LHC, and because, as David was reminding us, we're all on pins and needles waiting for the results to be announced from the analysis of the data taken so far. And this year, next year, is really the most, I think, the most exciting of the years for the discovery potential for new particles that we haven't seen yet for the LHC. I thought I'd just spend a little bit of time telling you about the LHC and telling you about the discovery of the Higgs, just a little bit, in order to put what's coming next into a better frame. So that's a picture of the area outside Geneva, Switzerland. That's Lake Geneva. Of course, from the air, you don't see this big red oval on the ground. Okay? But around 100 meters underneath where that red oval is a big tunnel and a big ring. And around that ring, one set of protons are accelerated to 0.9999999 times the speed of light. Another set is accelerated in the opposite direction. And they smash into each other in order to probe the laws of physics at distances around 1,000 times smaller than the nucleus of the atom. So what it looks like actually inside the tunnel, you can see the curvature of the tunnel. It's around 27 kilometers around. And this is a theorist's conception of what happens at the LHC. Now you have to apologize what a terrible artist I am. So here is a picture. Every time I look at this picture, I remember I have to fix it. You see, this is a magnifying glass, and I'm looking at a proton, but somehow, well, anyway. So this is a magnifying glass looking at a proton. And if you look inside a proton, you see that it's actually a messy bag. It's a bag that contains lots of quarks that are held together with gluons. The bag is around 10 to the minus 14 centimeters big. So you take this one bag and you take another bag and you accelerate them to this ridiculous fraction of the speed of light and you collide them together. Now, what happens most of the time when you smash those bags together is the bags just disintegrate and the debris from the collision goes in the direction that the beams were coming in. Okay? So that's what happens the vast majority of the time, and that's not the aspect of the physics that we're interested in. We want to know what happens at really tiny distances when these elementary underlying quarks and gluons bang into each other. And we know that they are doing that, they're having a head-on collision when the stuff comes out at a big angle relative to the beam. Okay? So we look for things that come out at big angles relative to the beam. And these energies are probing distances around 10 to the minus 17 centimeters. Something new happens here. And of course, we might make some new particles. They don't come out wearing name tags saying what they are. They typically decay in a time of order 10 to the minus 27 seconds back to ordinary particles like electrons, muons, quarks. Well, we never see the actual quarks. They turn into jets of strongly interacting particles. And in order to discern and see what happened to those very tiny scales, we have to surround the place where this collision happened with enormous detectors, giant detectors, in order to catch everything that comes out and try to learn something about what was going on in the underlying process. Now, it's a paradox of these machines. These are the machines that are probing the tiniest distances that we've ever probed, and they're the hugest machines that we've ever built. What's the origin of that paradox? Once again, it's Heisenberg's uncertainty principle. To probe really high energies, we read really short distances, we need really high energies. That's why we have to make the ring so big, just to be able to accelerate things at such incredibly high energies efficiently. And also we have to surround them with huge detectors because the particles are screaming out with huge energy, so we just have to stop them with like 5 meters, 10 meters of lead and other things in order to be able to study them and figure out what they're trying to tell us. All right, so here's a picture of one of the, it's a schematic of one of the detectors, the Atlas detector. So in here is where the collision happens. A proton comes in here, protons come in there, and here where the collision happens, and you have this big onion-like structure. It would take a whole lecture to talk about all the beautiful things that go into making this work, but which is supposed to capture all the particles that are coming out. And here, for scale, are some human beings. And that's an actual picture of the Atlas detector. Okay? And there's a standard European Union issue person sitting there, okay, in order to give you an idea of scale. So that's one of the detectors. The other detector that does exactly the same kind of physics is the CMS detector. The CMS stands for compact muon solenoid. The compact is because it's so much smaller than Atlas. Look at that. And this person is so much bigger, relatively speaking, than we saw relatively. I'm kidding. Okay. Okay. So now, how is the Higgs seen at the LHC? Do you think? Well, we have to bang particles into each other. We have enough energy that we can produce new particles, particles and antiparticles, or single particles if we don't have any electric charge, as in the case of the Higgs. And it's an easy matter. So here I have a proton comes in, another proton comes in, and the dominant process actually ends up being a little bit indirect. A gluon in one of the protons and a gluon in another proton pop out of the vacuum a particle that many of you haven't heard of probably, the top quark. But the top quark being popped up as a virtual particle out of the vacuum, the reason the top quark is important is that it has a very big interaction with the Higgs. So it's the biggest way that we can make a Higgs. Okay, great. You do all this work, you spend billions of dollars, you make a lot of Higgses. And actually back in 2012, when the discovery was made, they'd made maybe around 500,000 Higgses. Okay? Great, that's a lot of Higgses. Well, why do they have to make so many? Why don't they just stop at like 10 or 100 and call it a declare victory then? Unfortunately, that 500,000 they made were mostly useless. Okay? They're mostly useless because when you make the Higgs, most of the time it decays in a way that's completely buried under ordinary processes that are going on at the LHC. Here's the dominant way that the Higgs decays. It decays to a pair of things called bottom quarks, a bottom and an anti-bottom quark. Again, most of you haven't heard of bottom quarks, but that's fine. You think, great, we have 500,000 extra bottom quarks around, but too bad, the LHC is making billions of those bottom quarks already. You don't have a prayer of seeing the 500,000 extra that you added. So what our experimental friends had to do was wait for the very rare fraction of the time, around 0.1% of the time, the Higgs decays into 2 photons. It's rare, but you can see it. And even here, ordinary processes make photons, maybe factor 50 times bigger than the Higgses do. But the reason you have a prayer to see the Higgs is that when they come from the Higgs, if you add the energies of the 2 photons roughly, the energies should always add up to the same thing, to the mass of the Higgs. So if you look at all the events there are, some of them should pile up around where the Higgs is. And that's exactly what happened. So there's the Higgs. That's exactly the energy, or more precisely something called the invariant mass when you put together 2 photons. And here's what it looks like, mostly nothing, and then this blip. Okay, and the blip is the Higgs. So the discovery of the Higgs was obviously a triumph for experiment. It was a triumph for theory. As Robert reminded us, it was 50 years between the prediction of the Higgs and when it was finally confirmed by experiment. And it's a reminder, as if we need it, but it's always nice to have it, that physics works. And that belief in basic principles paid off. See, that's what's so exciting about the Higgs, because I introduced the problem the Higgs was supposed to solve. If we just looked at the elementary particles that we had without the Higgs, there was simply no way of grouping them together in a legal configuration that matched what we were allowed to have for the interactions with massless particles at very high energies. We needed something else. And at that point, at any point when you're confronted in puzzles in theoretical physics, you say, oh, everything's wrong, we'll go back, give up everything, start from scratch, throw everything out. That's never how anything works. Okay? Things always work within a very constrained framework. It's much better to go back and ask, what am I allowed to do, which nature hasn't done yet? I haven't seen it do yet. Where we're allowed to have these particles of spin 0. We've never seen nature do it before. That's exactly one extra thing was all that was needed, and we got to turn that red into black. Okay? So now, of the things that nature can do compatible with this broad principles, we've seen the first new thing. Okay? And that's what's exciting about the Higgs. It's the first really new elementary particles we've seen. It's the first elementary particle of spin 0. That was that 3/2 guy alone, and we'll come back to it in a second. All right, so that's a summary of the story of the 20th century. So let me now talk about some of the 21st century frontiers. And the first one I will go through very quickly because Robert did such a nice job talking about it. It's that the idea of space and time is doomed and it has to be replaced by something else. There are many ways of seeing this. There's a very nice thought experiment if you try to use the same junky magnifying glass to probe what's going on in a very tiny region of space and time. You need higher and higher energies to probe shorter and shorter distances. And in a world without gravity, there's nothing wrong with that. But eventually, when you have gravity, you have to put so much energy into such a tiny region of space that you collapse that region into a black hole. And all your efforts to learn what's going on in there are stymied. And if you get frustrated and build a more powerful microscope, a more powerful accelerator, what happens? You make an even larger black hole. Make it even harder to see what's going on at short scale. So that means that there's no operational meaning that we can give to the notion of distance and time and everything else when it gets to this famous Planck length. And every time that's happened to us in the history of physics before, that we can't even in principle give operational meanings to things, that notion has got to be replaced by something else. In this case, it's startling that it's space-time that's got to be replaced by something else. Now, the energy needed in order for this to happen is around 10 to the 19 times the rest mass, mc² energy of a proton. That's 16 orders of magnitude higher than the energies that we're probing at the LHC. Nonetheless, we can do these thought experiments. Something is going on up there, so something has got to explain this. And there are regions, as Robert also reviewed, as we go back very early time, when the curvatures of the universe become comparable to the Planck scale, or if you throw yourself into a black hole. If you throw yourself into a black hole, it's very much like being in a picture of cosmology in reverse, where there's a big crunch inevitably in your future. These are situations where theories just break down when gravity is strong and quantum gravitational effects are dominant. And even though we can't do the experiments practically, we can certainly imagine doing them, and we know that our theories just give nonsensical answers or no answers, so something else is needed. All right, but since Robert talked about it so eloquently, I want to spend longer talking about the second set of questions, and also because the second set of questions is more directly tied to experiment. And so this is the question, as I said, why do we live in a big universe with big things in it? A very simple, basic thing, but we have a terrible answer to this question. Now, the reason we have a terrible answer to this question is that the vacuum is too exciting. This is something that a very basic fact about quantum mechanics is that even the lowest energy configuration, you can have some energy. If you imagine a ball hanging on a string, in a classical world, it can be at the bottom and not move at the same time, so it has no potential and no kinetic energy. But quantum mechanically, you can never know both that it's at the bottom and that it's not moving because of the uncertainty principle. So there's inevitably a little bit of jitter associated with it, and the amount of that jitter is the famous Planck's constant times the frequency with which the pendulum oscillates. Now, let's imagine we're looking at a similar question where we're taking a box of the vacuum. Take a box of vacuum. Now, in that box, there are quantum mechanical fluctuations of everything there are. For example, photons can fluctuate. Electrons and positrons can fluctuate. The typical size of the fluctuations is given by the size of the box. Okay? And so the energy contained in these fluctuations is bigger and bigger as you make the box smaller and smaller. This energy, which is Planck's constant times the frequency, as the wavelength gets smaller, this energy is getting bigger and bigger. The box size is getting smaller and smaller, and so we have a terrible problem that if we look at just the energy density in the vacuum, the energy divided by the volume, then it's naively infinite. We have an infinite amount of energy in an arbitrarily tiny box. So that number seems to be infinity. Well, we just went through this big song and dance that space-time breaks down, blah, blah, blah. So probably we can't trust this picture when the distances involved become comparable to this Planck scale. We can do an estimate, though, right around that scale. And so we would get some energy density, which is the Planck energy divided by Planck volume. Now, what's wrong with that is that Einstein tells us roughly equals mc squared. Energy and mass are the same. Mass gravitates, so energy gravitates. And this energy in the vacuum should give rise to some curvature in the vacuum. Okay? Now, we don't need any fancy math in order to estimate how big that curvature should be, because the only scale that appears in this problem is the Planck scale. Okay? So the typical curvature involved should be around the Planck scale. That would mean that the universe should be curled up to be around 10 to the minus 33 centimeters big, or it should be explosively doubling in size every 10 to the minus 43 seconds. It's not doing either one of those things by a lot. So what do we actually do then? So, a good theoretical physicist should be able to estimate anything about the world. A decent theoretical physicist should be able to estimate anything in the world and get it right to a factor of 10. If you're Fermi, you get it right to a factor of 2. Okay? We're used to making predictions where theory and experiment in some cases agree to 12 decimal places. This is a case where you do a back-of-the-envelope estimate and it's off by 120 orders of magnitude. In public talks, I used to call it the biggest error in the history of physics. Then I realized I was insulting other sciences, saying someone else made a bigger error. No one has made a bigger error ever, okay? At least for an expectation of what you should see relative to what happened. The universe should be curled up to minuscule sizes, and it isn't. And yet we do all these fancy things, we make predictions, we discover the Higgs, we do all this stuff. We obviously have an answer to the question why the universe is big, so here's what we do. We say that there was indeed some quantum mechanical correction to the energy, some quantum piece, which in some Planck units we ask some graduate students to calculate, and they find that it's 2.6493718, blah, 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 and they work very hard and they calculate to 120 decimal places. And we say, thank you very much. There must have been some totally classical piece sitting there to the energy density of the vacuum, which was minus, what did you say it was? Minus 2.6493781. And then they agree for 120 decimal places, and they disagree in the 121st. Okay? Now, in 1990, as late as 1997, this was something many theoretical physicists would say it in a more sophisticated way, the deep symmetry arguments. Something should force that these two numbers are exactly equal and opposite to each other. And then there was a surprise from experiment. The surprise from experiment is that this number, the total number, was not zero. See, most theorists expected, because it's such a huge problem, there's some deep, mysterious reason why the final answer was precisely zero. Thank God for experimentalists who don't listen to us, because they went and they discovered that it's not zero. In fact, there cannot be some magic mystery mechanism that cancels them perfectly. They actually have to disagree in the 121st decimal place. So that's what we actually do in order to explain why the universe is big. Something as simple as why the universe is big, this is what we actually do. It seems ludicrous, and for obvious reasons, it's called fine-tuning. Now, there's a very similar, almost identical issue that's associated with the Higgs particle, and I can actually describe it in a similar language, and I'll come back to it in a moment in a similar language, but I want to describe it in another language that will be useful later. So the issue with the Higgs particle is related to why all the elementary particle masses are down with masses that are so much smaller than the Planckian scale. As Robert said, it's because the particles are so light compared to this Planck scale that gravity is such an incredibly weak force. And gravity being an incredibly weak force is responsible for why the universe can have big things in it. This tuning that we talked about is why the universe is big. The universe can have big things in it because gravity is weak. Otherwise, everything would be crushed under the weight of gravity into black holes. So why can the elementary particle masses be so small? Well, it's ultimately related to the mass of the Higgs particle. Why is the mass of the Higgs particle so small compared to the Planck scale or other very, very heavy scales in physics? Now, for particles like the photon, we have an excellent reason. Photons are massless, and we have an excellent understanding for why photons are massless. And the understanding has to do with the fact that the number 2 is not equal to the number 3. If in some approximation you imagine the photon was massless, let's say when it didn't interact with anything, it was massless, then you worry that when it interacts with all this roil of complicated virtual particles and antiparticles popping out of the vacuum, that could give it some inertia. Why couldn't that give it some inertia? Why couldn't that slow it down, make it impossible for it to always go at the speed of light? And the answer is that it couldn't, because 2 is not equal to 3. Remember that a massless spin 1 particle has 2 degrees of freedom, but a massive one has 3. And there's no way you can gradually turn 2 into 3 by slowly turning on these interactions. That's why massless particles with spin have this rigidity to them. Once you get them, you're stuck with them. Okay. However, that's not true for the Higgs. Again, that's related to what makes the Higgs so special. It's a particle of spin 0, and you've never seen a particle of spin 0 before. And one reason many people thought we wouldn't see a particle of spin 0 is that there's no reason it should be very, very light compared to fundamental scales like the Planck scale. Here, if the Higgs interacts with all this roil of mess of virtual fluctuations, there's no reason why it can't get a mass, because there is no difference in the number of degrees of freedom between a massless and a massive spin 1 particle, a spin 0 particle. 1 is equal to 1. Okay, so there we have 2 mysteries. Why is the universe big? Why does it have big things in it? And in both cases, what we actually do is we imagine delicate cancellations between things that have absolutely nothing to do with each other in order to explain these simple, deep facts about the world. Now, what could be going on? Could there be an explanation? Could there be a dynamical explanation? Sometimes an analogy I like to use is these fine-tuning puzzles. It's like if you walk into a room and you see a pencil standing on its tip within 10 to the minus 120 degrees of vertical, or 10 to the minus 30 degrees of vertical. It's consistent, it's possible the pencil is like that, but if you saw it, you would wonder, maybe it's hanging from a string, from the ceiling, or maybe you see a little hand that's holding it up, okay? That's what we're asking. Could there be there's a hand that's holding it up? And if we go back to the menu of things that's allowed, we see there's one last thing that is allowed, by the general principles, but which we haven't seen nature use yet, which is the possibility of having particles of spin 3 halves. And that's possible, but it's very special, and it requires nature to have an extra symmetry known as supersymmetry. Now, Robert referred to this, but let me say just a little bit more about it. We can think of supersymmetry as augmenting our ordinary notion of space and time by adding additional directions. So, but these additional directions aren't like our own directions of space and time. The distances in these extra quantum dimensions have the funny property that, that unlike ordinary numbers, where 5 meters times 1 meter is equal to 1 meter times 5 meters, the distances, let's say in the x and y quantum directions here, have the property that dx times dy is negative dy times dx. Okay? That's something that ordinary numbers can't do, but it's the sort of thing that we become used to in quantum mechanics. That in particular means that dx times dx is negative dx times dx, so dx squared is 0. And if dx squared and dy squared is 0, that means that a particle can't take more than one step in the quantum dimension. Okay, so you can't move continuously in the quantum dimension. You can move in the ordinary directions continuously. You can take a single step in the quantum dimension, and you can't take two. So when you take that one single step in the quantum dimension, what we see from the four-dimensional point of view is another particle with identical properties to the electron, but detailed things are different. Its spin is different. For example, if we have the electron, there's a partner, which is called a selectron, that would have spin 0. This is related to the possibility of having particles of spin 3/2 because this universal interaction that gravitation has between two electrons, when one of the electrons moves into the quantum dimension, turns into the interaction that it has with the graviton. When the graviton moves into the quantum dimension, they have to move in pairs, and so you have an interaction between an electron, a selectron, particle spin 0, and the partner of the graviton called the gravitino, which has spin 3/2. Okay. All right, now, how does this solve the problem? It solves it in a very beautiful way. See, our difficulty was that we have these violent quantum mechanical fluctuations. The fluctuations get bigger and bigger as the box gets smaller and smaller. But let's say when we get to sufficiently small scales, let's say short compared to 10 to the minus 17 centimeters, that's the scale that's associated with the LHC and the Higgs, and the problem associated with the Higgs. Let's say around there we actually see these quantum dimensions are there. Then there has to be perfect symmetry between what's going on in the quantum dimensions and the ordinary dimensions. And so that means that, that if it's going to violently fluctuate in the ordinary dimensions, it has to violently fluctuate in the quantum dimensions. But it can't violently fluctuate in the quantum dimensions. It can't even take more than one step in the quantum dimensions. Okay? So the only way you can have symmetry is if there is no fluctuations in the ordinary directions either. Okay? And technically what happens is that the presence of the supersymmetric particles eventually perfectly cancels those fluctuations. So this is the only deep mechanism we know of. You see, it's a deep problem. It has to do with quantum fluctuations in space-time. It stands to reason that if there's a deep way of removing it, you have to modify the picture of space-time somehow, and that's what supersymmetry is doing. Okay? It's adding these quantum dimensions. It's removing the possibility of violent quantum fluctuations, and it's the only mechanism we know of completely taming these violent quantum mechanical fluctuations. Now, supersymmetry could well have, and might still, be relevant for solving this problem associated with the Higgs. Okay? It could be that, that the Higgs and all the rest of the standard model particles are part of a super world, and all these violent quantum mechanical fluctuations that infect the Higgs are tamed by the presence of superpartners. And we could look for them at the LHC. When we bang particles into each other at sufficiently high energies, we could pop some of the ordinary particles off into the quantum dimensions and produce the superpartners. And when we produce them, they would decay back down to ordinary particles and some of the other superpartners in an intricate pattern of decays that theorists and experimentalists have spent a long time thinking about. This was the best candidate that people had come up with for 30 years of thinking about what's going on with this problem of the Higgs. 30 years of thinking about what could be the little hand holding up the pencil associated with the Higgs. This was the best set of ideas. But we haven't seen it yet. Where is everybody? Now, this is a little disquieting. Now, there's been a number of people who have studied this thing in more detail and more deeply, have not been terribly surprised with what the LHC has seen so far, not seeing the superpartners. And that's because in some sense, if supersymmetry was to perfectly solve the problem, it could have shown up already 25 years ago, or 20 years ago, or 10 years ago. It's not like everything was perfect until the LHC and then wham, our dreams were shattered. It's not like that. There is some element of it, of a little bit of disquiet. Not something terribly wrong, not something big wrong, but always something a little wrong. And what we're seeing so far from the LHC is just ramping up that a little wrong. It's getting more and more a little wrong. Okay? It is now the 11th hour for this idea. Not the general idea of supersymmetry. That's the last thing nature can do, compatible with general principles, all that's true. But if it's to solve the problem of the Higgs, it's getting to be the 11th hour for it to do so. That's why it's a very exciting time. 30 years of theorists thinking about this have yet to make one correct prediction. So what's going on? Are we theorists wrong by a little? Are we wrong by a lot? Like a whole generation of theorists were wrong. Everyone believed there was an ether a little over 100 years ago. All the most brilliant people in the world believed there was an ether, and they were wrong, even though it was a very good idea, and it led to important developments. The actual idea ended up being wrong. What's going on? Well, we don't know. That's the honest truth. We don't know. We're going to find out more from the LHC. But it's very important to figure out if we're wrong by a little or wrong by a lot. Okay. And something else that resonates with this is that this idea of supersymmetry, while very beautiful and the only idea that we know of that can remove all these violent quantum fluctuations everywhere, does not solve the problem associated with why the universe is big. It makes it vastly better, but it doesn't fully solve it. Okay? It takes this problem where we have to twiddle the dials to 120 decimal places, and it changes it to we have to twiddle it to 60 decimal places. But it doesn't solve it entirely. Okay? So that's another indication that maybe there is something even deeper going on. There's something beyond what most of us have been thinking about. All right, so this brings me to the final topic of the talk, which is the experimental future. We very lightly touched on the question of emergent space-time, and we spent a lot of time talking about why there's a macroscopic universe. And to me, it's fascinating that both of these questions, they might even be related to each other. Both of these questions indicate that we're clearly missing something huge about some combination of the three things: the quantum mechanics of a relativistic vacuum, quantum mechanics, space-time, and the vacuum. There's something in that triumvirate that we don't understand properly, that we need to understand better. And that's going to be a big motivation for talking about the next generation of big circular colliders after the LHC. So what we're talking about is another giant ring somewhere on the planet, maybe in Europe, perhaps in China, that might be around 100 kilometers around. In one phase, it could collide electrons and positrons, and in a very clean environment, produce millions and millions of Higgs particles, and allow us to study the properties of the Higgs in great detail. And in a later phase, we could collide protons, just like at the LHC, but with an energy of around 100 TeV. The LHC, I didn't tell you, its energy is around 14 TeV. So this would be energies more than 7 times the energy of the LHC, and push us further towards the energy frontier. So I repeat again that we're clearly missing something huge about the quantum mechanics of a relativistic vacuum. And to my mind, the Higgs is the most important elementary particle and experimental character in this mystery. It's the most important object that we can get our hands on and study that's relevant for these questions. One reason is, well, it's a prime participant in one of the mysteries. Why is gravity weak? Why does the universe have big things in it? Is the question, why is the Higgs mass so small? And that's the thing that we're not yet getting an answer to from the LHC. So we have to, this is a weird object. We've never seen an elementary spin-zero particle before, so we have to put it under a more powerful microscope. That's, I think, just experimentally obvious. You don't discover a new particle of the sort that you've never seen before and just sort of walk away with a vague understanding of it. Especially because the vague understanding is actually what we're going to get, unfortunately, from the LHC. So I told you that we've never seen something that looks like an elementary spin-zero particle. But how elementary is it? Well, there's a sort of if you have a particle that has some mass, there's a rough scale associated, length scale associated with that mass, which is Planck's constant divided by the mass times the speed of light. In the case of the Higgs, that will be around 10 to the minus 16 centimeters. In the case of the proton is around 10 to the minus 14 centimeters. And the proton, as we said, is not elementary. It's a big, messy bag. So the size inferred by this length scale is roughly the scale at which you see that it's a big messy bag. In order to decide whether something is elementary or not, nothing is ultimately fundamentally elementary as far as we know, but the reasonable question is does it look point-like on scales relative to this natural length scale associated with its mass? And what we're going to learn from the LHC, what we know now, what we're basically ever going to learn, is that the effective size of the Higgs is maybe a quarter of that. Okay? So it is looking more point-like, but not dramatically so, not like 1%. Okay? It's just like about a quarter of that scale. Now, that number a quarter is interesting because, in fact, we've seen other elementary particles before. The most important particle that in some approximation mediates the nuclear force between protons and neutrons is something called the pion. The pion, at first blush, also is a spin zero particle, and it's also a little bit elementary. Okay? So the rough scale associated with the pion is around 10 to the minus 14 centimeters. That's the size of the proton and the neutron. The pion is around 4 or 5 times smaller than that. Okay? So, and ultimately we learned that the pion is also made of quarks and antiquarks, just like protons are made out of quarks and gluons. Pions are made out of quarks and antiquarks and gluons. So it looks somewhat point-like, but not dramatically so. Ultimately, it is composite. And that's the story that we're going to have experimentally from the LHC. What we'll see is that the Higgs could be about as composite or about as elementary as a pion is. Now, if it turns out to be about that elementary, and in fact does turn out to be a composite, that would be very dramatic. That would already tell us something. It would be, to some extent, the replication of history, and we would look for some underlying quark-like objects or some other objects of which the Higgs is made, and that would throw particle physics down one trajectory. But if we look and we see that it's even more point-like than that, by an order of magnitude, then we're in essentially new territory. Experiments will have forced us into essentially new territory. And we have to decide that question. The LHC will not decide that question. The LHC was a spectacular machine for producing the Higgs and discovering the Higgs, but not for doing precision measurements of the properties of the Higgs. And because the Higgs is so strange, the precision measurements are what we need for progress. So this is the picture that we'll get actually from a Higgs factory. We have this 100-kilometer collider. We collide electrons and positrons and make millions of Higgses. Then we'll really see a picture that looks like really about like that. Okay? So it will look as point-like as that. Or we'll see some substructure. Okay? But one way or another, we'll know whether it looks point-like, and for sure, we'll know if it looks more point-like than a pion or not. Now, another crucial aspect of the point-like character of the Higgs is not just whether it looks point-like to other things. You see, everything that we talked about here, whether something looks point-like, one way of asking the question is whether it looks point-like when you look at it with light. Or we do fancier things like see how it interacts with two pairs of Z particles. Okay? But that's how the Higgs interacts with other things. Another crucial aspect of the point-like character of the Higgs is whether it looks point-like to itself. And that's actually something really interesting. We started the first part of the talk talking about this basic interaction between elementary particles, three things coming together at a point in space-time. But in fact, we have never seen the most elementary possible interaction there is, which is with one elementary particle interacting with itself. It turns out that this is actually impossible for any particle. Actually, it's possible for the graviton, but not for the standard interaction that it has. So we won't see that for a long time. It's not possible for any other elementary particle other than the Higgs. Okay, the only particle, an elementary spin zero particle, is the only thing that's allowed to have a pure self-interaction with itself. And if it's there, we'll know that it looks point-like to itself. So we're putting it under a microscope. Now, at the LHC, we won't even know whether this interaction exists. Never mind measuring. But if we go to the next phase of this 100-kilometer collider project, when we collide protons at 100 TeV, we'll make billions of Higgses. We'll make so many Higgses that we'll actually get to see this process. And we'll not only verify that this interaction exists or not see it, but if it's there, we'll measure it to 3% accuracy. So that's another big, those are the two guaranteed facts about this odd, strange object that Higgs are going to learn from these machines. We'll learn whether it looks point-like to other things, we'll learn whether it looks point-like to itself. Either the answer is no, that sends us down one way, the answer is yes, and we're really dealing with the absolutely strange and bizarre objects, the likes of which we've never seen before, and theorists will have to think much harder about what it's telling us. Now that's for sure what these machines will do, but of course this 100 TeV collider will also blast into the high energy frontier. Okay, that's the whole point. Before talking about what we're guaranteed to see or not see, the main reason all of us do this is the thirst for adventure, the spirit of seeing what's there at the frontiers, and there's absolutely no reason human beings should stop doing this now. And this collider will blast into the high energy frontier. It'll be capable of producing new particles with masses around 10 times the reach of the LHC, and crucially, it will probe these vacuum quantum fluctuations, these very things that are so worrying to us and so strange to us as theorists. It will probe them with a power 100 times that of the LHC. All right, so could these things actually happen? Given that thinking about these accelerators is a 20, 30-year process. They don't happen overnight. If they're going to happen, you have to start planning and thinking about them a long time in advance. And the last couple of years, especially between the two runs of the LHC, was an ideal time for many people to start actively thinking about this. And people have been actively and seriously thinking about it, and there are serious proposals on the table. Nothing makes a particle physicist happier than a map of the world with big rings on it. Okay? So here's a map of the area around Geneva again. There's a little dinky LHC, and this is what our friends at CERN are imagining. Okay? A 80 to 100 kilometer long tunnel. It might go underneath Lake Geneva. That might make some Genevans unhappy. But this is what they are seriously contemplating. They call it the FCC, for Future Circular Collider. And there's also a very serious and exciting proposal in China. I think it was David who first named it the Great Collider, which is, I think, a terrific name for the whole project. And again, there's a picture of the Earth with rings on the ground. This is there's actually perhaps some other sites that are now being talked about as well, but this was but this is certainly one of them at around 300 kilometers northeast of here in Qinhuangdao. There's a picture of a 50-kilometer tunnel and a 100-kilometer tunnel, and people have done civil engineering and more realistically looked at what these things look like, and you have even more detailed pictures of the Earth with big rings on the ground that make you excited and happy. So this is something that's being seriously talked about here. I spent a fair amount of time over the past 2 years interacting with many wonderful friends and colleagues here in China, and actually I've been amazingly impressed, excited by the vision and ambition they're showing in trying to pursue this. And I can also tell you that all of my young friends, theorists and experimentalists working in the field, have been tremendously energized by especially the Chinese proposal and the adding extra seriousness to the possibility that it might actually happen. This project the effort is being led by Wang Yifang, who's the director of the Institute for High Energy Physics in Beijing. And there's lots of really good info on the Collider project on the IHAC website, if you want to go there. Yifang is a very distinguished experimentalist who made an important breakthrough in our understanding of neutrino physics, and he's spearheading this effort. Now, let me just end with just a few vignettes of what this Chinese project could do in more detail. The electron-positron collisions, where we make millions of Higgses, is called the CEPC in China, for Circular Electron-Positron Collider, or Chinese Electron-Positron Collider. And this is the Higgs factory. They're imagining that it might be running by 2030 or so. And you don't need to look at this in any detail, but this is a measure of the accuracy with which we'll know how the Higgs interacts with other things, how the Higgs interacts with the Z particle or the photons and so on, compared to what we'll know from the LHC, even after the LHC is all done running. And you see, across the board, there are improvements by an order of magnitude, sometimes by a factor of 20 or 30. So again, as I told you, this will tell us if the Higgs is really elementary or not, okay? Or if it's more elementary than anything we've ever seen before like it. The 100 TeV version is called the Super Proton-Proton Collider, SPPC, or Assignment Proton-Proton Collider. Okay? This will go to the 100 TeV frontier, they imagine, by the early 2040s. As I mentioned, this machine just blasts into the energy frontier. So here's a picture. So there's nowhere for supersymmetry to hide. If supersymmetry is around, maybe, remember I told you as theorists, we're not sure if we're making a little mistake or a big mistake. Okay? And the LHC could finish running, and we could not be sure if we're just making a little mistake or not. There's some little detail, something we didn't understand. Okay. Either the SPPC will see supersymmetry, or we're making a big mistake. Okay? And we can know that. And the reach for producing these supersymmetric particles is a factor of 5, 6, 7, sometimes 10 or 20 times higher in mass than what we can get from the LHC. Now, why isn't everyone screaming ahead to do a project like this? Well, one issue is that it costs a lot. It costs 10 billion in your favorite units. Okay? And this is a slide that Yifan made a long time ago, which was I thought very illuminating to me, which is that it's a lot, but it's not a lot on the scale of what people have historically spent on machines like this. China got into particle physics back in 1984, building a 250-meter electron-positron collider in Beijing. Okay? Okay? That was done with around 10 to the minus 4 of Chinese GDP in 1984. And that 10 to the minus 4 of GDP is roughly how these accelerators have always cost everywhere around the world. And the CPC and the SPPC are costing around the same thing. But of course now, instead of building a little 250-meter thing to get into the game, this would be the machine that leads the world and is the future of the subject for the 21st century. And so, certainly in my view, I think the view of almost everyone who's thought about it, this great collider is, first of all, great for physics. Now, I don't mean just having this collider somewhere in the world. That would be amazing, period, of course, wherever it is. But having it in China has two extra things going for it. One, it's great for physics. It's great for physics because we would engage this ocean of talent in this country, scientific talent in this country, in our exciting adventure, 400-year adventure, 2,000-year adventure, depending on where you want to start, of pushing back the frontiers of our knowledge of the fundamental laws of nature. Of course, China is doing a lot of this already, but if we're going to if the world is going to take another leap like this, we need fresh blood. We need more people engaged in the field, and this is the most obvious country in the world to provide that large new pool of talent. So it would be great for physics. At the same time, it would be great for China. It would be great for China for many reasons. Obviously, it would be great to take on a large, ambitious project like this and bring it to fruition. And interacting with the whole world and having thousands of people come and work together on this project, I think would represent a really exciting spirit of collaboration between East and West on really unprecedented scales. And I really want to emphasize how international these things are. Okay? This is a picture. It's actually back from 2008, just right when the run of the LHC, right when the LHC started going. This is the distribution of all CERN users by nation. Okay? And so, you know, there's this huge number of people, of course, over 8,000 people all told. And they come from all around the world, of course, including China. And this picture, this map, is only going to get more and more colored as things proceed. Okay? There's no way these facilities happen without cooperation from the entire world. And any country that hosts it will be a magnet for drawing talent and people and inspiration from around the world. Finally, about the Great Collider, I should say that there's a wonderful popular book that's been written by Professor Yao, and I encourage you all to read it. It's available in Chinese. I read it in English. Apart from making a case for the Great Collider, it's actually a wonderful introduction to the history of particle physics, and not a very long read, but it's a really terrific little book, and I strongly recommend it to you. All right. So let me finish by reiterating that I think, in the minds of many of us, this is a singular time in the development of fundamental physics. The questions on the table are the deepest ones, the underpinnings of space-time, the origins and fate of our large universe. They're not little detailed push-forwards from the things that came in the last 10 or 20 or 30 years. I think these are questions, we'd have to go back to the 1930s, 20s and 30s to come up with questions that had the same level of deep import and ultimately philosophical impact on the way we think about the universe. The questions couldn't have been even meaningfully articulated 50 years ago. You know, it's one of the most important things in science. You can think about the really great big questions, but your job is to solve the next question. Okay? You can't spend all your time gaping in awe at the mystery of the universe. You have to do the thing that's in front of you next. And so 50 years or 100 years ago would have been the wrong time to answer these, to ask these questions. But today is the right time to ask them. There's nothing standing between us and them anymore. We finally have the theoretical framework that lets us properly pose them. And we have fantastic experimental probes on a number of fronts, including, as I've just said, the exciting prospect of giant new circular colliders. And so I'll just end by saying that to me it's an exhilarating time to be doing physics. We always have to take the next step. But this is one of the few times in the history of our subject where the next step is likely needs to be revolutionary and will not be incremental. And there's theoretical aspects of this, many of which Robert alluded to in his talk, but there's also important experimental ones. And I'll end by saying again that with the Great Collider, China can play a huge role in leading this adventure in the 21st century. Thank you very much.
Okay, I think we have time for one or two questions. Again, hopefully from non-string conference participants. Yes?
Thank you, Professor. I have a question, very concise. If the energy is very dense locally, since we are expecting to have colliders with higher and higher energy, and will we generate black holes that is not so tiny? And what will high energy physicists predict if that happens?
Well, so first of all, First of all, it's the most obvious place where you make black holes is if you collide particles with energies comparable to this Planck scale. We're not anywhere near that. We are, 16 orders of magnitude removed from it, and if we build this Great Collider, we'll be 50 orders of magnitude removed from it, but it's not going to happen anytime soon. If we do it though, if you imagine making a collider like that, you made a little black hole. Little black holes are not very qualitatively different than elementary particles. In fact, they'll just very rapidly decay into ordinary particles.
Professor, you just said that it's important to mix time and space, right? So do you really understand time? I mean, what is time? Is time fixed or does it evolve with something else? Thank you.
One of the things in this business is to get, you rapidly become suspicious of any human language. There's all kinds of questions that sound like profound and interesting questions, phrased in English or Chinese or any other language. But words are slippery, and you can spend a long time sliding around them without really knowing what you mean. So let me try to be precise. Sometimes we say things like space-time is doomed or is gone, and you're going to be replaced by something else, right? On the other hand, obviously there's such a thing as time. We're born, we die, etc. etc. Okay? So there's a useful notion of time. I forget who it was that said time is what stops everything from happening all at once. Okay? So there's a useful notion of time. What's interesting is that these precise notions, while in previous theories of physics, our colloquial notion of time is closely connected to some precise notion of time in the equations. What we have evidence for is that time and space should probably not occur in the more correct equations. But the only way we'll be sure that the more correct equations are right is if they give us something that looks exactly like time and space in the ordinary situations where they're supposed to apply. It's in weird places, like when you jump into a black hole or at the Big Bang or other things like that, where these notions break down. So asking a question like, what is time really, what is space really, I mean, they sound like really nice questions, and philosophers have spent thousands of years thinking about them. But professional physicists have not spent thousands of years thinking about them. In fact, they mostly haven't spent any time thinking about them because they're not forced to until very recently. And we're forced to very recently for very esoteric reasons, which are very important. But as I said, the only way, and you can come along tomorrow with a theory. Plenty of people do. I don't have space. I don't have time. Look how weird and cool my theory is. And no one will pay any attention until you show that in an ordinary situation, when you kick a ball, the ball moves on a trajectory that does what Newton said, never mind what Einstein said, never mind what everything else. So the notion of time and space is incredibly useful, and it's an indication of the magnitude of the challenge. That if it's not really there, we have to understand how come it looks like it's there so perfectly in almost all the situations where it's happening.
Thank you.
Maybe one more question?
I have a question. Do you think building a collider is the only way to develop new physics? How about we can develop new physics like astrophysical or cosmology?
Yeah, no, there are definitely other important frontiers in fundamental physics, but there's a very specific. And that's what I was talking about in this. I mean, we should do all the possible experiments we can. That's a big difference between experimentalists and theorists, is that experimentalists will often do the experiments they can do because they've learned to build some new cool thing that does the measurement much better than other people could. And that's great. Lots of progress has come from just doing things like that. There's a growing movement of people who are finding interesting ways of probing with tabletop experiments, probing various more exotic aspects of physics that many of us think might actually be there beyond the escape. What's important about the collider is it's a clear, important frontier, and you get some unambiguous data from it that tells you something for sure if you do the experiment. I mean, and it's not, you see, it's not at a random scale. It's precisely at a scale where we're deeply confused by something. If I could give an analogy, it's like I talked about the ether. People were confused about whether there was an ether in they thought it was there, but experimentalists went to look for it. And they built sort of precise instruments to measure the drift of the Earth through the ether. And the early experiments were sensitive to drift effects that were of order the velocity divided by the speed of light. The velocity of the Earth, let's say, through the ether divided by the speed of light. None of those things saw anything. That was already disquieting, was already weird. But it wasn't a nail in the coffin, because there are plenty of theories that predicted that you should see it at order b over c squared. So what was important about the last generation of experiments is they put the nail in the coffin. They went to order b over c squared and they saw nothing. And that was extremely important. Okay? I don't know whether our current ideas about what might be going on relative to the Higgs are more like the ether or more like something that ended up being right. But we just have to wait a little bit longer. We just don't know. But it's not a random thing. We're not just fishing in a random place. It's directly related to one of the, two very deep theoretical issues that's confronting us. So that's what makes the collider special. But absolutely, there's beautiful experiments in cosmology. There's a host of interesting tabletop experiments that probe fundamental physics in different ways, and they're all important.
Thank you.
Okay. One more question.
Thank you, Professor. Thank you for wonderful lecture. I have a question. If one day the string theory develop more major and successful and can be tested by the experiment and the string theory correct, whether physics find more fundamental theory, for example, back to quantum ether to information. Some physics think the materials is information and the information is materials. How do you comment on these values? Thank you.
Oh, I'm not sure if this is what you're referring to, but there's some very interesting. Correct me if I'm wrong, but I think you're referring to the idea that we know there's many very interesting exotic quantum states of matter, ordinary matter that people can engineer in labs, and that this matter can have features that look, at long enough distances, they look like ordinary particles and things like that. So could it be that something like that is underneath the patterns and structures that we see, not supersymmetry and string theory and the rest of it? That's at least in my own view, that's something very, very unlikely to be correct. And it's actually really interesting because lots of what goes on in that part of physics, studying quantum phases of matter, is totally fascinating and very closely related in ideas and tools to things that quantum field theorists and string theorists use. In fact, a lot of people go back and forth between the two fields. But there is a big difference in our world, which makes it special. We're not a garden variety quantum mechanical system. That's what I was emphasizing in this talk. We have quantum mechanics and relativity. And it's the quantum and relativity that's so brutal. It's very unlikely. No one has come up with any plausible way that some underlying material, which would have a rest frame, right? This is the old idea of the ether. In fact, it's amusing that the more recent versions of these ideas that many people have been talking about are very closely connected to Maxwell's old model of mechanical ether. Maxwell had a picture of ether with cogs and gears and wheels all working together. And these modern quantum ideas are sort of quantum versions of that picture of the ether. Well, the ether worked in a lot of ways, even led to the correct equations of Maxwell, but it was not there. And it's not there because of relativity. Relativity is a deep thing. It's not, and it doesn't seem to arise accidentally. And so that's what seems to make that entire approach a non-starter. Unless someone comes up with a brilliant idea for how something that has an underlying ether nonetheless gives you something that looks perfectly relativistic at long distances. It seems very unlikely, and no one has come up with one so far. But that's the main stumbling.
Thank you, and let's all thank Nima again for a fantastic lecture, as well as Barbara.
Also, I propose we give a big hand to our chair this evening, Professor David Grove. Thank you. Thank you for coming.